Welcome back. In today's lecture, I am going to talk about the orthogonality. Okay, and it is possible to show that orthogonality plays a very important role in order to solve some kind of engineering problem related to mathematical modeling, problem related to some kind of physical modeling, or other branches of the applied means applied physics, applied mathematics, or applied engineering. Okay, so orthogonality is very important concept, and we have already seen whatever I have written here, that orthogonality is the mathematical formulation of the geometrical property of the perpendicularity. Okay, so if I have some kind of vector like column vector where everything is form of numbers, real number, then during our school day we have already seen that how using some kind of dot product one can talk about the perpendicular, two things are perpendicular, two vectors are perpendicular or not. And what we have seen that if their dot product equal to 0, then that two vector are perpendicular. Suppose that if I will consider these two vector 1 0 and 0 1. Okay, and if you take the dot product of these two, then that equal to 0. So in that way we are telling that these two vectors are perpendicular. Okay, but what happens now, we are actually generalizing our vector. Now instead of real number, we may have some kind of function, we may have some kind of polynomial, it might possible I have matrices. So I have to again redefine the orthogonality, and means we have to redefine the perpendicularity. Okay, so or we have to generalize the perpendicularity. Okay, and using orthogonality it is possible to show that we are just generalizing the perpendicular notion of perpendicular. So whenever we are talking about two vectors are perpendicular, at that time we are using dot product. So and we have already learned that generalization of dot product is nothing but inner product. So due to that reason, now I am going to do inner product, and after that we are trying to force or trying to check that inner product equal to 0 or not. If that is 0, then two vectors. Okay, now vector is very generalized, so both are perpendicular. Okay, and in algebra what we found that whenever we are talking about vector space and whenever we are talking about element, so any space, suppose that if we are talking about some kind of a space where each element is represented in form of functions. Okay, so I have infinite many element. Okay, similarly, suppose that if we are talking about 3-dimensional, 4-dimensional, n-dimensional plane, so I have infinite many element. And what we found that using the concept of linear independence and linear combination, I can able to define some kind of concept where using minimal number of vector we are able to express or able to travel anywhere inside the space. And I have already taken the very simple example of the two-dimensional space where you can take any two linearly independent vector. Obviously very simple vector is this. Okay, and if you take real number as a and real number of a b and take the linear combination of these two, then you are able to get any ab inside this whole space, anywhere you can able to travel. And these two vectors are linearly independent and able to span the whole space, and due to that reason that is called basis. Okay, now I have infinite many way to select basis inside that space. Okay, but actually it is possible to show that if I select some kind of mutually orthogonal element inside the basis, then we are getting some extra advantage. Okay, so in this lecture we are going to identify those kind of advantage, and after that we are also going to see that is there exists some kind of algorithm if I have some kind of basis vectors that is not orthogonal to convert them as a orthogonal vector. Okay, so I have some kind of information of non-orthogonal element inside the basis, and using some kind of practical numerical algorithm we are trying to convert that vector as a mutually orthogonal vector. Okay, so first we have to identify why that is very important and why we are trying to do that, and how to do that. After that, in last we will do. Okay, and I hope that some of you, those who are working on machine learning, those who are working on data driven or applied mathematics, they are already well aware about some part of that particular algorithm, because that algorithm is very famous and very much useful. So we are going to see that algorithm in today's lecture using the help of linear algebra. Okay, so what is basic application of orthogonal basis? So there are several applications. Okay, so and one of the most important application is Fourier analysis. During Fourier analysis, nowadays you might have seen that whenever we are storing the data, so data might be in form of audio, video. So at that time also it is possible to show that whatever element we are using, that is orthogonal basis only. Okay, after getting some kind of data, we are doing discrete Fourier analysis, inverse discrete Fourier analysis. So everywhere these kind of things, where proportion means orthogonality play one of the very important role. Okay, so now similar kind of things I have actually written here, that inside Fourier analysis decomposes a signal into simple periodic component, and we have already learned from the first year onward that whenever we have some kind of periodic signal, I can able to express that signal in form of sine and cosine, which are orthogonal system of function. Means if you see the sine and cosine, then that is orthogonal with respect to each other, means their inner product equal to 0. Okay, so now let us directly come to the orthogonal or orthonormal basis. Okay, so orthogonal we have already defined that we have to just check the inner product of two vectors, and after that we have to show that that equal to 0, then that two vectors are orthogonal to each other. Okay, and now we are trying to understand that what is meaning of orthonormal vectors or bases. Bases means why we are just concentrated on bases, because if you know the basis of some space, then you are able to express any element of that space. So there is no need to worry about all vectors, just you have to worry about the basis. Okay, and due to that reason, now I am going to define the orthogonal and orthonormal basis only. Okay, because if I know basis, I can able to travel anywhere inside the space. Now what I am telling, that let V be a real inner product space. Why real? I have written real means I am assuming that all element inside this space are just a real number. Okay, some kind of real number. So real number or real valued function, whenever matrices, then that contain real valued matrices. Okay, now we have already know that whenever two vectors of this space, that V and W, if I will take, and both are orthogonal if their inner product equal to 0. So I will calculate the inner product, and after that I will keep that equal to 0. Okay, and a special case of inner product we will know that is nothing but the dot product. Okay, so those who have any confusion on inner product, I have already recorded that lecture and already we have discussed. Okay, so please again go through that lecture. So in this case, vectors in the Euclidean space, suppose that now if I will confine myself in Euclidean space, means where each entry is just a real number, then orthogonality at that time we are just talk about the dot product. Okay, so inner product at that time, that is very special, that is we are if I have Euclidean space, then we can just able to talk about the dot product, and at that time we are telling that two vectors are orthogonal if they will meet at the 90-degree. Okay, but if I will define the generalized inner product, okay, at that time I cannot talk about like that they meet at the right angle. Okay, now a particular important configuration arises when V admits a basis consisting of mutually orthogonal element. Okay, so now actually what happens, that I have some kind of a space V, and V contains some kind of inner product space. Okay, it means that I know that how to define the inner product, how to define the norm inside that space. So I can able to talk about closeness of two element also. Okay, so that is the meaning of the V as inner product space. And after that, what I am telling, that minimum number of vector from this space V I will select, and using that vector I am trying to express the all other vector of that space, and that is called basis. And I am assuming that I have selected those kind of base element of basis that is mutually orthogonal. And if you see the two-dimensional space, so I have already given the example that is like that. In three-dimensional space, I have 1 0 0 0 1 0 0 0 1. Okay, so this is one set of the orthogonal vectors. Okay, and that is going to form the basis in three-dimensional space R3, and this is R2. Okay, now could you please anyone comment that suppose I have three-dimensional space. Okay, so inside three-dimensional space, obviously I have infinite many way to select the basis. So is it possible to show that number of orthogonal basis, that is finite or infinite, that is only unique orthogonal basis, or do I have infinite many orthogonal basis? Anyone, could you please comment about that? Suppose you can just consider the R3 space. So what we found, that this is one of the orthogonal basis. So this is only unique orthogonal basis, or there exist more than one? What do you think? Obviously basis is infinite. Now I am just talking about very special class of basis where all element inside the basis that is mutually orthogonal to. Okay, so how many that kind of basis can exist inside one space? What do you think? Finite or infinite? Anyone, could you please comment? Manish, Kumar, are you here? Kunal Kumar Verma, Kunal, are you here? Simran, okay, so could you please comment how many basis, how many mutually orthogonal bases are possible inside some space, suppose three-dimensional space? Finite or infinite? Okay, yeah, so Simran, that might be infinite. Okay, so our goal here, that how to define infinite many orthogonal basis. Okay, that is our goal. Okay, so it means that I have to search some kind of algorithm. If I have some form of basis, so from that basis I can able to convert some kind of mutually orthogonal basis. Then our job is solved, because we already know that if I consider that any three linearly independent column vector, okay, that serve for the basis. Okay, so here one of element 1 0 0 0 1 0 0 0 1 I have selected. Now what you can do, you can consider any 3 cross 3 matrix for the three-dimensional space. Okay, and it is possible to show that if their all column vectors are linearly independent, then that serve for the basis of that particular space. And now what we have to do, we have to just convert that basis into orthogonal basis using some kind of standard algorithm. Then one can claim that if number of bases is infinite, then similarly I can able to find those kind of bases which are means those kind of bases where each element is mutually orthogonal element, that is also infinite. Okay, so in today's lecture I am going to check that. Okay, now before going to that, I am going to see what is meaning of orthogonal or orthonormal basis. I have already told you that why we are just focusing on basis, not on the orthogonal vector, because if I actually know the basis, I can able to express any element inside this space. So I am going to define the orthogonal and orthonormal. So what I am telling that, suppose I have n dimensional inner product space. Okay, inner product space means I have vector space, and after that I know that how to define the 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 length of the vector. Okay, and in order to define the length of vector I need the norm. Okay, and norm, how to form the norm? If I have some kind of inner product, and if I take the inner product with same element, and if I take the square root of that, then that is form the norm. Okay, so I am talking about the inner product space, and I have, suppose I have this kind of basis vector, so that is called orthogonal basis if that will satisfy this kind of condition. So if I not equal to j, and at that time I have to just check that this relationship hold. Okay, if this relationship holds, then I can tell that that is orthogonal. Okay, and basis is called orthonormal. Apart from that, if I am able to check that their length is unity. Okay, and in order to check that length I need the notion of norm or notion of inner product space. Okay, and due to that reason I am working with the inner product space. So in order to check orthogonal, again I need the notion of inner product space, and in order to check the unit length I again need the notion of the inner product space. Okay, so these two are the definition. Means whenever I am talking about orthonormal, at that time orthonormal basis, then that should satisfy this condition, as well as their length of the vector that should be also unity. Okay, so now you are able to easily able to comment that whenever I am talking about a standard basis, okay, a standard basis means I have Rn space. So in Rn space, one of the simplest basis is 1 0 0 0, E2 is 0 1 0 and 0 0 1. Then I can able to represent any element inside this n dimensional space, and it is possible to show, since here this is Euclidean space, so either I can able to talk about the inner product, standard inner product, or dot product, both are the exactly the same. Okay, and now due to that reason I am not going to bother about the inner product, I am just going to talk about the dot product. Okay, so if I take the dot product, and if I calculate the norm here I am talking about the very standard norm, two norm I am taking here. So suppose a b c d, so a square b square plus c square plus like that, so that is unity. So due to that reason this basis n dimensional space, so this basis means this standard basis is actually orthogonal as well as orthonormal basis. Okay, anyone has confusion in definition? Okay, if you don't have confusion, now what I am going to do, I am going to generalize it. Okay, what I am telling that, suppose v1 v2 and vn are an orthogonal basis. Okay, and how to check that is orthogonal basis? What you can do, you can take any two element inside that particular basis, and after that what you can do, you can calculate the inner product. If inner product, and we know that one can define inner product in infinite many ways, so you have to talk about orthogonality about some standard inner product space. Okay, or so if you change the definition, it might possible that one set of orthogonal basis vector that might be orthogonal in some specific way when you define the inner product, and in some other way if you define that is not orthogonal. We have already checked that kind of example, okay, when I was dealing with the inner product. Okay, so please again check that. Now whenever I have orthogonal basis, it is possible to show that just by normalizing it. And how to normalize it? You can take that particular vector and divide that vector with norm of that. Okay, and norm I can easily define. I have told you that if I know the inner product, then you can take inner product of same two function and take the square root, then we can be able to define the norm. Okay, and this is called the orthonormal basis. It means that if I know the orthogonal, then just by doing this kind of normalization I can able to get the orthonormal basis. Okay, and here I have taken very simple example. So I have these three are the basis in R3. How to check this is the basis? I have already told you that first you can check that these three are linearly independent. And how to check these are the linearly independent? Just basically, so you can solve this equation alpha 1 and alpha 2 and alpha 3 and v3 equal to 0. If that will imply alpha 1, alpha 2 and alpha 3 equal to 0, then I can tell that this is linearly independent. Okay, and since I have three-dimensional space, so three linearly independent vectors can form the basis. Okay, in that way you are able to check that this is basis. Okay, now after that, once you understood that this is the basis, then you have to check that that is orthogonal basis or not. So for that, what you can do, you can select any two element and take the dot product of that element. Okay, so if their dot product equal to 0, and why I am just worrying here about the dot product, you can see that I have column vectors. Okay, and all are the real numbers. Okay, so I can treat that as a Euclidean space too, and that space I can just define the standard dot product. Okay, so similar kind of things I have done. Okay, so from an orthogonal basis with respect to a standard dot product, we are basically telling that okay, these three are the very standard basis with respect to the 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 dot product. Okay, and all are orthogonal, means each element inside the basis are means orthogonal. Now I am going to convert into orthonormal basis. So how to convert it? Just you can take the standard norm. So standard norm, again I have to calculate the norm, and norm is 1 square, 2 square and 1 square. So here root 6 I have, and due to that reason I have divide like this. Okay, so this is very simple exercise. So if I have some space, and I have identified some kind of basis, and if I know in advance that that basis is orthogonal, then I can able to convert as a orthonormal. Okay, and how to check that is orthogonal? Okay, if that is Euclidean space, then simple dot product you can take. If that is not, then you have to do some exercise. Okay, now what is another proposition is telling? Suppose now v1, v2, vk be non-zero mutually orthogonal element. Okay, and if vi is not equal to 0, because whenever we are talking about basis, so no element inside the basis should be 0. Okay, because using the linear combination I am expressing the all other element of that space, and due to that reason, that is actually this assumption is obvious assumption that whatever element of the basis, that should be non-zero. Okay, and after that you can see that here, since this is orthogonal, so this condition is also obvious that their inner product vi vj, that should be 0 when I not equal to 0. Okay, so what we are claiming, that if v1, v2, vk that is mutually orthogonal, and if they will satisfy this kind of property, then that is also linearly independent. Okay, so I have to prove that v1, v2 and vn or vk, you can tell that is linearly independent. So how to prove that? What you can do, you can just express in terms of linear combination. So how to express in terms of linear combination? You can take a scalar c1, c2, c3 and cn and multiply this. So this can be expressed as a linear combination. Now what you can do, you know that the any two vectors inside this space, whatever I have defined here, that is orthogonal. So you can take the inner product with some vector v1, and after that apply the property of linearity of the inner product. We have already seen the property during whenever I have defined the inner product, so that is actually homogeneous. So same property I have used here, and since all other part are orthogonal, due to that reason that is 0, so only one part is going to remain here where both vectors are the same, and due to that reason I can express ci, and after that norm of vi square. So and I have told you that whatever set I have considered, where I am assuming that no element is 0. So if no element is 0, then I have only one choice, that ci not equal to 0. Similarly, I can able to prove that c2 not equal to 0, c3 not equal to 0 by taking the inner product with suitable vector v1, v2, v3. Okay, now suppose, now what I am going to do, I have taken some kind of vector space, okay, and vector space is P2. What is meaning of P2 vector space? I am telling that each element inside this vector space, okay, each form of some kind of quadratic function, quadratic polynomial, okay. So I have some kind of, means each element of this space can be represented like this, okay. And after that, now since I am going to talk about the orthogonality, and due to that reason, first I have to define some kind of inner product, okay. So whenever I have column vectors and each entry as a real number, so we have already seen that how to treat that, okay, using dot product also we can treat. But here now entry is different. I have entry as a some kind of quadratic polynomial, and due to that reason I have to define some kind of standard inner product, okay. So since this is continuous function, and due to that reason, if you remember the class of inner product, at that time I have talked about L2 inner product, okay. So L2 inner product of two vectors can be given like P and Q is vector, so I have to define definite limit between A to B, and after that we have to take Px into Qx and into dx. So similar kind of things I have done, and in order to define the norm, I have told you that you can just replace P by Q by P, and after that you can take the square root. So similar, so in this way I can able to define the inner product, and I can able to define the norm, okay. Now here you can see that if I see this quadratic polynomial, so here where means in order to form this polynomial I have some kind of basis, okay. So any element for this particular space can be represented with the help of 1x and x square, okay. You can take any element in this space. So due to that reason, these three sets of the functions, okay, that is going to form some kind of basis, okay, and that is also called monomial. So these monomials can form some kind of the standard basis, but if you check this basis, so these bases are not perpendicular or not orthogonal, okay. So since whenever I am talking about dot product and Euclidean space, I am just talking about the perpendicularity, and their generalization is called orthogonality. So I have to talk about orthogonality, and how to check orthogonality, I have to calculate the inner product between any two vectors, okay. So I have identified the element of basis 1x square, and I have already told you that basis, because using basis I can express anything, okay. So 1 and x, and after that I have substituted here in this, because in this way I have defined the inner product using L2 norm. So just I have to substitute here 1 and x, and in this way if you solve it, then you can see that nowhere that is 0, okay. So it is possible to show that 1x square, okay, whatever basis, so that basis is not orthogonal basis, okay. So it is possible to show that if you are trying to find some kind of orthogonal basis, then you have to do something here. Without doing anything, I am assuming that I am going to express same quadratic function using another set of the element, and that element is also orthogonal, okay. So how to construct that element, we will see algorithm for that. Before seeing the algorithm, I am telling that, okay, suppose in arbitrary way I have selected these three elements, okay. So now I have quadratic polynomial, but I am going to represent every quadratic polynomial using these three vectors: 1 x minus half, x square, x minus 1 by 6. Now it is possible to show, if you take these three vectors in the basis, then their inner product, and how to calculate the inner product space using L2 norm, using this norm, okay. Then it is possible to show that now that is 0, okay, inner product is 0, and whenever inner product is 0, then I can conclude that these three vectors, okay, and where a space is polynomial, so all three vectors, okay, are going to form some kind of orthogonal basis. And in order to form the orthonormal basis, what we have to do, I have to calculate the magnitude, or I have to calculate the norm. And how to calculate the norm, since I have already defined fix the inner product, so corresponding to inner product I have to fix the norm, okay. and I have to calculate that particular norm, and after that we have to just divide the orthogonal basis with that particular norm, and in this way I can able to get orthogonal basis. It means that if now I have a space, okay, suppose that a space consisting of polynomial functions, anything, then also I can able to form some kind of orthogonal basis. Okay, so this is a small exercise. Now what I am going to do, that computation in orthogonal basis, one of the challenge, that how to calculate the orthogonal basis. Okay, so first we have to check that why I will calculate, why I will do that. Okay, so first I have to check the advantage of orthogonal or orthonormal basis over the general basis. Okay, so if you check the practical example, then it is possible to show that once one has a basis of a vector space, a key issue is how to express other element as a linear combination of basis element to find their coordinate in the prescribed basis. Okay, so if you remember the previous lecture or previous to previous lecture where I am talking about coordinate and basis, then what we have to do, suppose we are in three-dimensional space, okay, and I have identified this as a basis, ABC, DEF and GHK. So these three are the bases. Suppose I have identified. Now suppose if you have to express this element, okay, so once after fixing the basis, so this kind of basis, and suppose if you fix this basis 0 0 1 and 0 0 1 0, I have fixed this kind of basis. Suppose if I have to express this element, so expressing this element using this basis is easy. Why? I will I will actually project from here to here, and I will identify x, and that kind of multiplication if I will do here, then I can able to get the x coordinate. Okay, after that I will keep the projection here, and in this way I can define coordinate y, and similar kind of things I can able to do for z. Okay, but whenever I have general kind of element inside the basis, and this basis you can see that this is orthogonal or orthonormal basis. So whenever I have orthonormal basis, then finding this element, and this element is called coordinate. So if I have any vector v and I have to express that vector, then apart from basis I need the coordinate, and once I fix the basis, then coordinate is unique. Okay, so finding coordinate is relatively easy. Okay, but if I will just start with the general basis, then finding coordinate is very difficult, and due to that reason, that is one of the basic motivation to talk about the orthogonal and orthonormal basis. Okay, so same kind of things we have written here, that if you are going to start with the general basis, then you have to solve the algebraic equation. Okay, algebraic equation. And what kind of algebraic equation? Suppose this basis if you fix, then I have to solve a dash plus b dash plus c dash, and suppose I have to express alpha beta gamma, then you have to solve this in order to find the coordinate of a dash, b dash and c dash. But here solution, suppose that now if I have to express alpha beta gamma, then solution is very easy here, x equal to alpha, y equal to beta and z equal to gamma. Due to that reason, handling anything with orthogonal and orthonormal basis is basically computationally efficient. Okay, and easily one can do that, and due to that reason people are trying to search the orthogonal and orthonormal basis. Okay, so now what next theorem is suggesting, suppose u1 u2 and un be a orthonormal basis for a inner product space. Orthonormal basis means if you select any two element inside that basis vector, then that is their inner product equal to 0, and if you check the length of any vector also. Okay, so I have defined the inner product, and corresponding to inner product I have defined the norm, and if I select the norm, then that is equal to unity. And so if you have orthonormal basis, then one can write any element in the linear combination of this, where c1, c2 and cn are called the coordinate. Okay, so and we have just discussed that what is meaning of coordinate using the three-dimensional space. Now finding this coordinate c1, c2, c3 are very easy. How to find that coordinate? You can see that ci here, that is nothing but v means original vector you can take, And after that, what you can do, you can select ui, and I you can vary from 1 to n, and after that you can take the inner product. Okay, so you have using inner product, easily you are able to find the coordinate. Okay, so if you have orthonormal vector, okay, so if I have orthonormal vector, then coordinate system is very easy to find. Just using the help of inner product, I can able to find it. Okay, and where now you can see that one more thing, that I can also able to define the norm, because I know the inner product. So norm definition is also very easy, because each vector has length unity. So if I will define the actually length of that vector, so a square of first one, a square of suppose if I will select using Pythagoras theorem, I am going to define the distance or two norm like that. So c1 square, c2 square, c3 square, it is possible to show that since all other quantity had unity length, so I can just, if I do the square of each and every coordinate, then I can also able to define the norm. Okay, so in this way, if I have orthonormal or orthonormal basis, then process is very easy. Okay, now now what I am telling, that suppose that instead of orthonormal basis, suppose if I have just ortho means orthogonal basis. Okay, orthogonal basis means length of each element is not unity. Okay, then also it is possible to show that finding coordinate system is not so difficult. Okay, so first what I can do, since I have written here that if I have some kind of orthonormal basis, then c1 c2 cn can be given like this. Okay, so I have to prove this. Okay, so how to prove that? So proof is very easy. What you can do, you can select any element v. Okay, and since u1 u2 and un are the basis, so I can tell that any element can express with the linear combination of that. And after that, you can apply the concept of orthogonality. And orthogonality concept, we already know that if two vectors I not equal to j, then that equal to 0. If I equal to j, then that is equal to 1. And after that, you can apply the concept of bilinearity. So if you apply the concept of bilinearity, it is possible to show that again you can able to recover ci, because this is the orthonormal, means this is the orthonormal orthonormal basis. So orthonormal basis means any two bases, their inner product equal to 0 and their length equal to unity. Okay, and in this way you are able to prove. Similarly, you are able to prove the norm also. And how to prove norm? You can start with v square. V square is nothing but the inner product of two same vectors, and you know that these two vectors can be represented like that. And after that, you can just open the bracket, and after that you will get this. So in this way you are able to prove. Okay, now what I have done, I have actually taken the orthonormal basis. So I have three-dimensional space, and in three-dimensional space, it is possible to check that these three actually vectors can be form orthonormal basis. And since here you can see that each entry is real, so I can use the dot product also. That is not a problem. So if you calculate dot product of u1 and u2, that is 0, and u2 and u3, that is 0, u1 and u3, that is equal to 0. Okay, and after that, it is possible to show that if you just take the standard norm, so a standard norm, that is also unity. So due to that reason, these three vectors are actually form orthonormal basis. Now what I have to do, in three-dimensional space, suppose I have this 3 point 1 1 1. Okay, I have to express the coordinate of this point with respect to this basis. Okay, it means that this vector I have to express in terms of these three vectors. Okay, so one way you can solve the algebraic equation. Another way, so how to solve algebraic equation? You can just equate v equal to c1 u1 plus c2 u2 and plus c3 u3, and after that, you solving algebraic equation, you try to find c1 c2 c3. Obviously that is not a so easy job. Okay, but using that theorem, easily you are able to find. What you can do, you can select the vector v and take the dot product with u1. I have already told you that why dot product is okay here, because I have column vectors and each entry is just a real number. Okay, so I can able to define norm as a 2 norm. Okay, now that is 2 by root 6, v equal to 3 by root 5, and another coordinate v equal to u3 as a 4 by root 3, and in this way means very easily I can able to express v and their coordinate is like this. Okay, so due to that reason we are trying to find the orthogonal or orthonormal basis. Okay, so what we found that if I have orthonormal basis, okay, then things are very easy. Using inner product concept of inner product, I can able to define the coordinate. Suppose that if I don't have if I have not orthonormal basis. Orthonormal basis means length of each element of basis is also unity. Suppose that is not there, I have just orthogonal basis. So then how to find the coordinate? It is possible to show that at that time also finding coordinate system is not very difficult. Again inner product, but now since this is not length is not unity, so you have to normalize that length by corresponding norm. Okay, and in this way, even if you have now orthogonal basis, then also you are able to find the coordinate of the any vectors or any element with respect to some kind of standard basis, and here basis I am assuming that is orthogonal basis, not orthonormal basis. So orthonormal basis, then this is just unity, and if I have just orthogonal basis means dot product of any or inner product, sorry, inner product of any two element is 0, then using this way I can able to find the coordinate of a1 up to an. Okay, and means in this way norm also I can define. Okay, so proof actually remains consistent like the previous case. V, then I have two vectors, so you have to take the inner product of that, and it is possible to show that is like this. Okay, now suppose I have four vectors. Okay, so four vectors, and how to check that is going to form the basis in four-dimensional space? What you have to do, you have to just prove that alpha 1 v1, alpha 2 v2, alpha 3 v3 plus alpha 4 v4, that equal to 0 implies alpha 1 up to alpha 2, alpha 3, alpha 4 all are equal to 0. So in this way it is possible to show. After that, since I am talking about orthogonal basis, so orthogonal basis means you have to take the standard dot product. Here I can take because here just I have column vector. Okay, now you can see that I have to find the coordinate. Okay, so in order to find the coordinate, in previous theorem what we found that if that is just orthogonal, then in order to find the coordinate system a1, so in order to find a1, here I have to calculate the inner product of v, means this whole vector with vi equal to 1 and vi v1. If I will just try to find the first coordinate, then everywhere I have to replace I equal to 1. Okay, so replacing I equal to 1, first I have to form the v1 square, and how to form norm, using that I can able to form the norm also, and after that just what we have to do, I after taking the inner product I have to divide with that norm, and in this way I can able to find the coordinate of any point very easily. Okay, so in this way, suppose that if I have to express any vector with respect to some kind of orthogonal basis, then easily I can able to do. Okay, now let us come to the some other case. Suppose now here I have some kind of a space where each element in form of some kind of quadratic polynomial. Okay, so I have second order quadratic polynomial, for example, and just in the just now what we have checked, that if I will select this kind of element 1x square, then that will not form a orthogonal basis. Okay, because if I define the inner product like this, then what happens that by defining inner product like this, what I have, that I have actually 1x that is not equal to 0. Okay, so but if I select or restate the basis in this form 1x minus half x square x by 1 by 6, then that is going to form some kind of orthonormal orthogonal basis. Okay, now what I have to do, I have to find coordinate system c1 c2 c3 using the above formula. Okay, so what I have to do, I have to find the norm. So L2 norm I have to find, and after that I have to just what I have to do, I have to check, since or in order to find the P1 C1 coordinate, I have to take this whole polynomial, I have to calculate the inner product with P1, and after that just I have to solve it. So if you solve it, then it is possible to show that in this way I can able to find C1, C2, C3. So just you have to actually solve this kind of definite integral. And suppose now if you have to express this x square x plus 1, okay, and suppose this kind of polynomial you have, and you want to express that polynomial in terms of some kind of quadratic polynomial where actually basis is mutually orthogonal, then you have to find the coordinate system c1, c2, c3. So I have fixed the polynomial. Okay, so suppose if you fix the polynomial px as x square x plus 1, then c1, c2 I can able to find like that. C1 is 11 by 6, c2, and in this way I can able to express the polynomial. Okay, now one of the very much use of this concept is like that. Suppose that I have some kind of some kind of function or some kind of polynomial, so I am going to express that whole space, whole vector space, using some kind of trigonometrical polynomial. Okay, and that space I have represented like t and power n. Okay, so I have some kind of n dimensional space, and now what I am going to do, I am going to express that space using the help of some kind of trigonometric polynomial, means in form of sine or cosine. Okay, so I have defined like this: summation of a j k sine x power j cos x power k. And degree I am assuming that I am going to consider, since I have some kind of a space, so in order to form the space I have to consider all polynomial which order is less than equal to n. If that is strictly equal to n, it is possible to show that it is not going to form some kind of vector space. Okay, please check it. Okay, so due to that reason I am going to consider the order that is less than equal to n. Okay, now if you just see the individual monomials, so that is not going to form the basis. Okay, and due to that reason I have to construct some kind of basis of this space. Okay, and one of the basis, it is possible to show that if I construct like 1 cos x sin x, cos 2x sin 2x, cos nx sin x nx, then that is going to form the basis. Okay, and in order to form the basis, just I have to check the linearly independent element. Since this is n dimensional space, so it is possible to show that here if I will select these 2n plus 1 functions, so using that 2n plus 1 functions I can able to express any element inside that space. Okay, so by seeing that space, but if you see the dimension of this space, so this dimension of this space is 2n plus 1, because dimension is number of element inside that basis. Okay, so again what I am going to do, I am going to define the L2 norm, L2 inner product. So L2 inner product I have defined like that. Norm is also required for me, and due to that reason I have defined the norm. And after that what I am going to do, I am going to consider cos kx and cos lx. So that is 0 to pi pi. Just please see, check the definite integral. And during the Fourier series you have already seen this kind of thing. Due to that reason I am not going to discuss much. Cos kx and sin lx, so here minus pi to pi, that is equal to 0, and similarly cos kx into cos lx equal to 0. So check these kind of things, and after that norm I have calculated like this. Okay, so what I am going to generalize here, that any polynomial, okay, so I have some kind of a space, okay, Tn space, and I want to express that space, and suppose that whatever function inside that space is periodic of period 2 pi, then it is possible to show that I can express that particular function or polynomial using the help of the trigonometrical function sine and cosine, and that is nothing but the Fourier series. Okay, so now one of the challenge, that how to find a0, ak and bk. Okay, and that challenge is actually solved by the inner product. Since cos kx sin kx all are orthogonal basis, so whenever I have orthogonal basis, so we already know that how to find the coordinate system, and due to that reason most of time students are actually remembering this kind of formula and they are finding the coordinate system. But now you are able to understand that why basically that formula comes into picture. Okay, so that formula is just due to the obvious consequence of the linear algebra. And what linear algebra is suggesting us, that whenever I have some kind of a space, and if I have some kind of orthogonal polynomial, so and if I want to express any element using the orthogonal polynomial, then finding the coordinate is very easy. You can take the inner product of that particular function with the first means element of the basis, and after that you can divide the norm of that particular basis, then you are able to find the coordinate system. Okay, I will again reinterpret this in terms of perpendicularity in the next class. Okay, similarly I can able to find ak and bk. Okay, and this is nothing but the Fourier series. Okay, now up to here what we have just seen, that I have some kind of a space. Okay, and we are able to see that what is advantage if I want to express the element of that space using orthogonal basis or orthonormal basis. Okay, so if I have some kind of orthonormal basis, then finding coordinate system is very easy. Okay, suppose that even if that is orthogonal basis, then with help of inner product or norm I can able to find the coordinate system. So one of the obvious consequence, that finding coordinate system is very easy, and whole proof of the Fourier series or motivation of Fourier series is basically based on that one. Okay, so Fourier series is not come automatically. They are actually fully motivated from the concept of the orthogonality or linear algebra. Okay, so now one actually job is still remaining, that is very important. Suppose I know some kind of actually basis, and that basis is not orthogonal or orthonormal. Okay, so now is there exists some kind of numerical algorithm or some kind of actually practically implementable algorithm such that I can able to convert that non orthogonal or orthonormal basis into orthogonal and orthonormal basis, and it is possible to show that that kind of algorithm is actually developed in 18th century. Okay, again that algorithm is developed by Laplace, and finally that algorithm is actually rediscovered by Graham Schmidt. And this process, that if I have some kind of basis and that is orthogonal basis, so that is not orthogonal or orthonormal basis, to how to construct that is actually given by this algorithm. Okay, so since I don't have time today, so due to that reason I will discuss this kind of algorithm in next class, and after that I will again proceed towards the further more relevant result in direction of orthogonality, and after that I will express the use of orthogonality for different processes like least square estimation and other possible applications, whatever that is very relevant for the engineering application. Okay, so now it is time to conclude the lecture. So what we have seen in today's lecture, so in today's lecture we have basically trying to understand the necessity of the orthogonal or orthonormal basis for some system. Okay, or some kind of a space. Okay, so what is basic idea, that if I have some kind of orthogonal or orthonormal basis, then finding coordinate system is very easy. Okay, so due to that reason orthogonality is very important concept. And after that what we found, that now suppose if I have to express anything in terms of polynomial, and suppose I have some kind of periodic function of 2 pi, so what we found, that by identifying any basis, and after that now I have also one of the algorithm to convert that basis into orthogonal or orthonormal basis, that we are going to learn in next class. So using that I can able to express the any kind of functions which is quadratic function or some kind of quadratic function, just with the help of some kind of periodic function. Okay, so that kind of idea, or it is possible to show that idea of Fourier series, Fourier transform, Laplace transform, all are somehow connected. Okay, or obviously the assumptions are totally different in each and every series, but everywhere concept of orthogonality plays a very important role. And due to that reason we have to learn orthogonality, we have to appreciate orthogonality. Okay, so with this remark Now class is in from my side. If you have any specific question, then please let me know. Okay, if you don't have any question, then I am going.